Hello and welcome back to another episode of Learning Rust with Good Oxide. Hey Sid.
Hey Sebastian.
And today we leave boxings and lifetimes and boxes and trade objects, which I think was kind of a tough topic behind. And yeah, it's a fun topic, but kind of still tough because these trade objects, they are a bit magical. They feel like it. They're a bit, even to me still kind of knowing what they are. I think without really seeing how it's implemented, I always feel there's a tiny bit missing, but I can use them, so it's okay. So today I thought we look at conversions, because conversions happen a lot. We have already seen conversions in one place at least, which is that question mark operator, right? Like foo something, because this can actually convert the error type into another error type. And I think that's probably where most of the time you want to use conversion traits.
Haven't we also seen it in the collect function? Doesn't that also do a conversion? Or it can do a conversion at least?
No, it does not. It converts, I mean, it produces something new that wasn't there before, but it's based on, I think, preset implementations of, oh, you want a vector of t or a vector of something that is a result of t and e. And then you have special implementations for this stuff so that the compiler knows what to do. But here, you are in control. Here you define if and how conversions happen. And let's see if we can have a look at this. So do we have question mark operator usage here? Yes, we do. So as you can see here, add 1 actually gives us an out of bounds error, but somehow this question mark operator is able to create an anyhow result. And that is of course defined somewhere. It's not just magic, it's just predefined. And let's see if we quickly find that. I'm looking for from. Can I jump to the code, please? Oh, yeah. So maybe it's implemented here. And here we go. So this anyhow result has an error in it, right? And the try operator, or this question mark operator, is calling the conversion of some error e to get that error type that it wants. So it doesn't convert the value, it only converts the error, right? So it looks for an implementation for all things that are, and here's the constraint for all e's, where e is a standard library error, and a send, and a sync, and a static. So send sync we ignore for now, that's all about multi-threading, but this essentially means it's a fully thread safe thing that you can that works perfectly with threads in every way, and it's fully owned, so there are no references to something else. And this is the kind of error it wants to see to have a conversion working. And you see all it does is it says give me an error from standard error, and then here you have the same thing happening again. The same type constraint, the same generic, so that it just dynamically does something with it. So here we have quite some magic with unsafe. Don't use unsafe. I don't think we ever talked about it. Probably will never will. No need for it really. But this is how it does it. You know, it does some smart stuff that is based on knowing a lot about how this is supposed to work. They mention V tables here, which it creates itself even. So it's kind of a virtual lookup table. This is probably the kind of manual and super optimized form of using trade objects. So trade objects also have a V table inside, and it's a fancy way of boxing an error. Like so. I mean, can I? Yes. edit this file. So what it really does in its own way that you probably will not ever reproduce and don't have to is doing std error. This is what it does, because that gives you this trait object, object that now allows you to store this error in a way that doesn't force you to exactly know the compile size of the error in your own type. Because remember, type self here is an error and it does not have a generic type parameter. And this tells you it forgets about the actual type and hence the actual size of the error that goes in. And it does that by effectively boxing the error. But it knows in the moment you convert, right? So at some point it has to know, because it then takes it and moves it onto the heap, and then it forgets about it to be able to store it in itself. Where is, yeah, see? So again, very, very special and fancy. I don't know. It definitely is a good reason for it, but just imagine this as box std, dune std. Yeah. Okay. We dug deep into anyhow here. Just to reiterate on conversion traits and that it already happens, because this from trait has been implemented. So maybe this is something we can do, but not with errors. Let's keep it simple. Struct A and struct B. And now we have struct A, and we want to be able to convert a B into A. That's simple. And now it says, I can't do it because you want to say, I implement from. Yeah, from what to what? From.
Yeah, actually, you would probably implement it for B, right?
From B and for what?
Then for A.
Yep. That seems like the right way to go about this. And yeah, we don't really have any data, so we can just say for simplicity's sake, okay, these are convertible, and see it like this. That's a state machine now, right? You can implement valid state transitions with types that way. And you can't possibly get it wrong because the type transitions are implemented here. Same goes, I mean, enumerations you can of course do very similarly. And it's interesting because that's one way of writing it here. But I could also write from, B, A from B. Because this function is now available on all A's that have a B in the from spot. So that function is generic and you can have multiple implementations of that. So if you had a C, of course we can do the same thing. And you see it's happy with that.
Okay, so you are using specific types here in these implementation blocks. But I'm guessing you could also then switch that to generics with constraints, basically. So you can do these conversions more generically. Yeah.
Yes, definitely. Like you've seen in that anyhow example. Where it says, okay, for all E's that are this, that implement these traits. Whenever I say that are this, that have these traits. And lifetimes. So lifetimes are part of the generic specifications, like the set of things that implement these three traits and that are not referring to anything borrowed, but are self-contained, thus static, or are referring to things that are static, right? So that's always worth remembering. So you can, of course, have static strings inside of that error. That doesn't make it less static. It's just still as static as it was before. This was always something that, you know, this took me a long time for me to realize, to sink in, because lifetimes you think are always only with borrows, but they're not. Like this lifetime is attached to everything that is fully owned, even though there's no borrow inside. Just because it's a signal to the compiler about the lifetime of that thing, the maximum possible lifetime, and that's pretty neat. Okay, so now we already have 2 implementations for A, and 2 ways of calling this. Like this into, right? Can I also do this here? So yeah, let's fix this unused stuff by using an attribute here, allow unused everything. That should, so that's crate level here. Now it's on the struct. Now it's on the crate. So the parent, so to say, on the entire crate. This is because it's the main module. And now it should not.
Useful.
Yes, that's pretty cool about linters. They can be really annoying, and the Go linter, for example, is super annoying, and it's literally in your way. Like, oh, there's an unused import, and it's an error, right? And you have that all the time when you just comment out code, and then you have an unused thing there, and then oh, come on, and you have to comment that out as well, and it's constantly bugging you. Whereas here, it's just a warning, which is the right thing to do, but also that you can disable, which is what I do a lot as stuff is in progress. So it's really a way of working. You can do this also to say, I want to deny missing docs. And now you see, now you have to document your stuff. But I could
be... That is pretty cool.
Yeah, that's what I do a lot too. But then as I work through different modules, I usually, within modules that I want to go to later, I say allow missing docs. So temporarily I, allow certain things so that I can focus on one thing at a time and don't have to do everything at once. And that's neat too.
Yeah, it's essentially switching work modes, right? You can kind of just help yourself getting through a certain task.
Yes, and always useful, really. It's the way to go. By the way, you have allow deny, which you can, allow can be or deny can be overwritten by allow, or allow by deny. You can just switch them on and off that way wherever you are. But there is the forbid as well, and forbid permanently disables a certain thing. So that's usually what you do, in your state, in your crate, to make a statement. Forbid unsafe code. Never ever can you use unsafe code in this crate. And that is actually something that is picked up by Cargo Audit or Cargo Geiger, which looks for unsafe code. And it displays. Can I get this to work real quick? Okay, no. But it displays, okay, maybe here. It displays all the crates and the dependencies, and will show a little green icon there if you don't have unsafe and if it's forbidden to have ever unsafe. So these clean crates, they're pure Rust. They're particularly, safe, so to say, because we consider Rust in itself safe, even though it's built on unsafe, of course. Okay, it does start a compilation here, and it takes a while, but not today. Just saying, cool things can be done that way, but I use it mostly for unsafe code. There's also deny Rust 2018 idioms. So that's old ways of writing certain things that you shouldn't write anymore. And you forbid it like this, or you deny it at least. I think I have forbid here even, because you never want these and it's better without them. So It's usually this. In a decent crate, you have at least this, and probably also missing docs. Oh yeah, I can't say that here. And of course you can do that as well. Then it's a bit more concise. Yeah. Attributes, pretty neat. And with this, I think you know everything already. That's attribute. Mostly. Okay, so apparently this into here is picking up on the from implementations because it can do C into and B into, and I didn't implement anything. So this thing does some magic here to kind of turn my from into an into, like change direction, right? Like here, A from B or B into A. Right? Like you read it and it's just, yeah, sure, B into what's on the left side, but you never specify what's on the left side. So some type inference must be happening here. Like if I remove this, then it doesn't know what to convert into. That makes sense. But is there a way like to specify that? Because this must be something generic here. Let's see if we can do that. But first, let's see how that works. Okay, so there's this one implementation here that implements the right thing. So two types, T and U. So we can do into U for any T where U implements from T.
Mm-hmm.
And as you can see, we say U implements from. This makes this callable. So you can say U from self. And that's into here. So it takes, consumes ourselves and then converts into U. Always. And this is how that works.
That makes sense. I think that's what I would have guessed as well, but it's still, yeah, kind of magically grabbing the type from the other side. But yeah, I guess that's the type inference.
Yeah, it's pretty cool, huh? The compiler must be able to see, U is returned, and what's the return? What am I assigning to? Yeah, this is how I can fill in U, and that's how it then propagates through this, and that's how it fills in all the missing types and can solve the puzzle of, yeah, figuring out types. That's type inference. And not all type inference works. If it's too many corners, too many indirections, so to say, of figuring out the type even though it's there, then yeah, it can't always find it. I have that sometimes you can, or you have to provide type hints. And type hints you can provide either like this by specifying a type on the left hand side where you assign to, for example. This is particularly important here. You can also, yeah, let's see. Can we make it work? Like, there is a syntax for this that I always kind of forget that allows you to completely specify what you want. So into U, huh? And U is the destination. So and the B is handed. Okay. So look, this first argument here is self, but this is actually the source. So in this case, this should be B. And even though self is always a bit magical because self is passed into itself, like it's hiding the first argument essentially, you can always write that out. You can always write A as into, and then we call into, wait. Oh wait, that's another one, huh? That's another implementation. Into, okay. See, this is what I mean. I always have difficulties to spell that one out. This convert, like this using as, it's basically a cast. See this as into, and then you can make a call on it. The problem is this needs some type parameters here, and it's still not happy. Interesting. What version of this do we have here? U4T. Okay, U from south. So we pass B, and B is actually here, huh? So can we just write this out? Into B? No, it's also, yeah, see, so I never get that right. Any hints? Like even the syntax, you know, sometimes you are able to specify the type here by just filling it in, but I think with these traits you usually have to use this casting, which sometimes is easy enough, but especially with the into, I'm always struggling. But from what I could tell, the from is implemented on the U, so oh no, wait. Yeah, no, U is A. So somehow it feels this should be like this. But also that does not work because, ah yeah, right. Syntax, better. Okay, now it works. Oh, I should still allow unused. Okay, and that's the way to write it. Excuse my...
So you're getting the into implementation for these two specific kinds, types basically, and then calling it with B.
I mean, what's so terribly confusing is that now it makes no sense anymore. Into A, okay, that makes sense, and then into B, because I have to pass B as first argument. So now we don't have an instance anymore. We don't have an instance of A, we just have the type into, and we pass it the source of the conversion, and then from is called on B. A from B. And that's how that works. But that's also how you can always write this. So you don't have to use this or rely on this on this inferred kind of writing, but you can. And that can be useful for your own traits one day. I never wrote one like this because it's most useful for conversions, and for that you always have from and into. This also means that in theory we can impl into A for B, right? Like the other way around. Can we? Let's see. Let's just try. And now we just pass A. Okay, but still not happy because we have a conflicting implementation. Into A for type B. Because
so it implements that automatically, basically when you do the from implementation?
Yes. Because we have this blanket implementation in the standard library, core. And that's this one. Look. Oh no, wait. It's not. Oh yeah, now it shows me the wrong one. This one. So you see, it's exactly this one that it finds. Impl tu into u4t. And that's already present, and this overlaps with our specialized implementation. Like we have multiple valid implementations now for the same combination of types. And that's a clash. And Rust does not allow that. Rust does not yet allow specialization. Think about it. It could be interesting to rely on this default, on this generic case, but also have specialized implementations that can be more optimal in some way. And that's particularly interesting. This is why you want that, this optimal or these specializations of trait conversions or of traits in general. But Rust currently doesn't allow that. It might already be available as feature on Nightly, because there is definitely an RFC for that.
But isn't there already a way to override implementations or like certain methods and implementations? I mean, I'm not sure what the difference is if you don't have a default implementation or you do, but I thought there is a way to override these.
No, like not with traits like this. No, I mean, also there's no such thing as overrides of methods. They're just implementations of traits, and there's only one of them ever for a particular thing. And with these generics, generics, they do cover a big spectrum of different types. And this means that, yeah, you might not be able to write a certain specialization just yet, even if you want to. But most of the time, you probably should just not, I mean, this is just not what you do, use into, because into is really just a utility trait that is mostly useful in this case, or when you have a function. So let's imagine the following, fn foo, and that takes an a, and you want to take all kinds of a. So for now, we just start like this and see how we could call that, right? So foo b does not work because it's a b, but how can I make an a?
You call into.
Exactly. I call into. And it infers the type, and I can do that for C too. But wouldn't it be cool if I could just write this, because it's essentially the same, it's essentially there. Can't I do the conversion for them?
Oh. Okay.
And now you see I just rebind this. I just do the conversion as the first thing. And now I can do all of these things.
You pass an A now?
Oh yeah, let's try that too. And also let's fix whatever there is here. Ah yeah, here. Type annotations needed. Because it wants to have something that converts, like it tries to resolve for the wrong type. Because A, it doesn't compute for this. I can't convert it into something that implements into A, even though A itself works. But it doesn't like that. Okay. This is how generics work here. And you could think, you know, there's this thing, trait objects. Can I use trait objects here? Can I use something like this? No. Because it's not a trait. It's just a struct. But if it was a trait, yes.
Okay.
And this is what we've seen, right? This is dynamic, or it's polymorphism. If you have these trait objects, then you can just easily create a trait object from anything that implements this trait. We've seen that in the example for iterators. Exactly the same thing. Where we seemingly take a reference of something that is an iterator and cast it, so to say, into a trait object. In this case, we have just good old generics, which are compile time evaluated things. So right now we have 1, 2, 3 different instances of the function foo. For each different kind of argument, 1. Because what you pass is still a b, right? So it takes the b, and this resolves to b, and then I say b into a. It's really like if you would fill that out yourself, right? So a is b, and then you say a into, like this. This is exactly what the compiler does. And yes, you can't have multiple of the same name. Makes sense. And that's it. So that's why you have multiple things. And this is also why, by the way, look, if there's now millions of lines here, then this one conversion causes these millions of lines to be repeated, right? Every time the compiler does this, millions of lines, copy, paste, copy, paste. And this is something to just be aware of, because these useful conversions for APIs, they're nice and they make it easy to use. Cool, that's what we want. But you want to be aware of the cost of this, because people don't usually want to pay in size. And that kind of accumulates. So what do you think would be a way to make this better? Like,
I mean, the way we had it before, right? Where you say you do pass in an A, or you expect an A, but you do the conversion with into from the outside. Or basically the user of the function has to do it.
That's okay, but I don't want to lose this. I want the user to be able to do this, but not pay the entire price. So now I deduplicated that, see?
Okay.
So I just do the conversion. Yeah. I just pass it on, so millions of lines once, and then this trampoline function here that just is the one you want to call. That's the nice one, and that's the inner version here. That is probably also private and hidden somewhere. That's not anything you expose. Yeah, and this is how you can also have a cake and eat it too, this kind of thing. Without only paying what you have to pay. Okay, cool. Now there's one more thing. I think that's already pretty much it. But also, what happens if the conversion can fail? Like, what if we have this enum A, and that is a B, or it's a D, but there's no C. Actually, let's just keep all of this as example. And then have one more, enum Z. Let me have an X, and then S. Oh, actually, we don't have to reinvent this. Let's have an A and a B, but no C. Okay. So now I want to implement something that is allowed to fail. So from A and B will always work. Oh, let's make it easier on us. Let's just implement A. Impl from A for Z. Oh, yeah, we never need that. Now we return the only thing that we can be right now. And that, of course, works. This is infallible, so nothing new here. But what if you want to accommodate for the possibility of this failing? Like maybe because there's some I/O involved, or there's something involved that might actually make it legitimately fail. This is a bit of a contrived example, because of course you just don't implement things if they don't work.
That's what I just thought. I mean, if there is no implementation for it, then you can't call it. So in my mind, it always works. But I'm guessing there are examples where it can fail. Good.
Yeah, let's call this parsed C, right? So if you parse something that comes from the input, then of course this can fail. Think about it from string. So now we have some string as input or just some bytes, and we parse them. So that's usually where you have this for, I analyze some input and then it might be valid, it might not be valid. And you have special functions for this. In like when you have strings, you can parse from that, and there's a trait that is called from string, and that allows you to call parse on things. Look at that before we go into this. It's kind of its own conversion, but it's special. It's just special because it's such a common thing to do. So let x be a u32, and then parse this. Does this work? Look at that, this works. So I was able to parse 8 into u32. And that parse is very, very similar to from as a conversion, but, or into, let's say. This is more like into. But it can fail. And I prove that by making this not so much a number. And now we see we have a parse error here, invalid digit. Okay. And this is the kind of behavior we can also have for our own conversion traits. And then it's called TryFrom instead of from, TryFrom.
The trait itself is called TryFrom.
Yes. So let's see if that, magically works. Maybe it does. No, because the trait from string slice is not implemented for u32. So they did not automatically implement that, even though they could have, right? They could have said, if there is this, and if it implements from string, then I can automatically implement TryFrom. That would work theoretically, but they did not do that. Probably there's a good reason for it. But whenever there's something from a string, you can just call parse, which is useful in many cases. Okay. So let's get back to TryFrom. And impl TryFrom C for Z. Let's see what the members are. Oh, now we have an error type. It's any error type, by the way. There's no constraint on it. Can be an actual error, std error, or unit, whatever you want.
Anything else?
Anything goes, yeah. And now we could just say, that never works. So return an error and then that error type that we declared. And let's see what happens now. So TryFrom A should work. CZ is a into. So that works. Yeah, I want to instantiate the A instead of calling a method on A, which I can. I can do this. Get me the A into and then put an A into it. Totally works. Which is, yeah, which probably we could have done here as, oh no, we couldn't have done that because we don't specify Z here. So Z is missing here. Huh?
True.
I was thinking what's the difference to here, but type is the difference. Okay. But that's more common here. And now I wonder, can I also use TryInto? So if into is implemented, is TryInto implemented? And the answer is yes.
Okay.
So there's some blanket implementation as well, right? So TryInto has this auto implementation similar to what into has. Let's see how that is implemented. So TryInto is implemented for all things that implement TryFrom. Okay, it forwards it to TryFrom. Let's see what TryFrom does. And TryFrom is probably auto-implemented for every U that implements into T. And in that case, error shall be infallible, which is a special marker that really just says it's infallible. This will never fail. It's a special type.
Okay.
I mean, not a special type, it's just a type that you've seen there. It's a marker. It's not actually special, it's just something you write in code that you use as such. And this will never
So
fail.
not an error.
Yes. There is no error, but you have to kind of handle it because the method signature tells you it's there. But you see there is no error case here. It's infallible. But it's auto-implemented for that reason. Because it kind of makes sense to automatically do that. Otherwise, you would have to duplicate all the work, right? You kind of have to do these things manually, which isn't practical. Okay, so now what about C? Okay, so that one, line 60, did not work because C always fails with an error right now.
Yeah, makes sense.
And sure, we could implement something that doesn't make it always fail or some logic there, but for the sake of the example, I think it's good enough. And that's TryFrom. That's the conversion traits here. And that's all you do with them. And they're really powerful and useful, and I use them a lot because people kind of expect that. If you have types that are convertible into each other, it's really good style to also implement the conversion traits out of the box because people might just want to use it like this. So don't invent your own conversions. A to B, A to C. You could, of course, but you should not.
Yeah, that's the thing. I think just usually you would do this in a different style. I don't know, you pass it into a function and then it puts something else out. But yeah, you just use into and then it's clear for everyone. And yeah, it's just known.
Yes. I mean, that's the Rust way, and that's the way, that's the way to write it. And you can write it very, very neatly. But also, it's a hidden thing, right? Like, this is hard to discover. Discoverability, think about it. Like, how do you discover this? Yeah, you don't. I mean, you can probably find parse here, but it's not so obvious what you parse into. So these things, they're not obvious at all. So for discoverability, it might still be nice for an API to have certain common conversions that people want. Like I have that, for example, like there's an object and you say to commit or into commit or TryInto commit. But you can also use into or TryInto to do this style. So we actually have both. Because in Git Oxide, if you have an object that is one of four things, right? Objects are tags or commits or blobs or trees. Then you can say, well, into tree. And I always forget like what is what. But some of these are infallible but panic. So if you really know you have a tree, you can just call into tree here. And this will either work or panic. Or you do TryInto tree and then it either works or you get an option back. So you have to still deal with the fact that it might not be a tree, things like that. But the same thing might be implemented with TryInto, for example. And then on the left side you have let tree be this. Things like that. So very useful to do, and both have their merit for sure. One is discoverable, the other one isn't, or only advanced users would write this because it's more idiomatic. You kind of want to write this if you can, or if you know about it. I think, yeah, discoverability.
Yeah, but that's also the nice thing. You can just try it out and see if someone already did the work.
Yes.
And it just works.
Interestingly, I don't usually do that. Like I myself, I mean, the first thing I do is to or into this is what I try. I want to see something complete there. In a way, you would land on this one if IntelliJ is smart enough to see that. Maybe you get lucky, but yeah, give or take, huh? but Idiomatic is this for sure. Yeah, I think that's all that comes to mind for these conversion traits, and a little bit of parsing as well for standard types. No problem. Cool.
Awesome.
Then this shall conclude our today's session. Thanks, everybody. Thank you, Sid. Thanks, everybody, for watching, and see you tomorrow. Bye-bye.
Thank you. See you.
Not tomorrow, actually, but some other day.